So of course, yesterday we left off with lesson 6, or sorry, we're in unit 6. We left off at lesson 6.3. So if we get rolling here, all right, let's look at Google Chrome here. Okay, so if we look at what we have left to accomplish just in this class here, okay, we need to cover the rest of unit 6, so that goes from 6.3 to 6.6, okay? Obviously 6.6 being our wrap up and our test for this unit here, and we'll get to that, okay? So again, obviously my goal is to try to get us through these 2 lessons here. If we can do it, 3, but it looks like we're on this pace of about 2 lessons each. So we're gonna do these 2 lessons, and then just like I would normally, I'll record a video lecture for lesson 6. We'll go through 6.3 and 6.4, and I'll record a video lesson for 6.5 and a little bit of review for 6.6, okay? So I'll record a video lecture assuming we don't get this far, and I will post that as kind of weekend homework. All right, so we've done pretty good so far of not having to have homework here, but apologies about this last one. All right, so that's our plan. Let's get rolling here. All right, so again, yesterday we introduced ourselves to polar coordinates. We introduced ourselves to polar functions, or functions on a polar graph, right? And so now we're gonna look at the polar form of complex numbers. All right, so again, we're gonna deal with complex numbers. So if we review what a complex number is, right, it's where we have a real part and an imaginary part. Right? We have a real part and an imaginary part. So we have an A plus or minus I times B, or B times I, right? BI. Where again, I is that square root of -1, right? I stands for the square root of -1. Okay. And again, BIB or BI, okay, that's our imaginary part here. Okay. And so what this is telling us is that we can designate on our polar coordinates here, we can designate the x-axis as our real axis and a y-axis as our imaginary axis. If we were to do that, we could represent our imaginary our imaginary number here by this vector. Okay, so we can show it here by this vector. All right, so again, if we had 3 plus 2i, right? We go to the 3 for the real, we go up to 2, right? Ignoring I, considering that this is the entire imaginary axis. And so we could find this 0.32 here, similar on our normal, Cartesian plane. Okay, so here, again, we can represent our imaginary number with a coordinate, just a comma b. All right, just a comma b. All right, so if we keep this in mind here, we can then do algebraic operations for complex numbers, okay? They're gonna be the same as we do for our vectors. Okay? They're gonna be the same as we've done for our vectors. So if I look at two vectors here, again, when I'm adding them together, I just add the A's and I add the B's, all right? Lo and behold, it's gonna be the same thing here. Right, so I'm gonna add my real parts, I'm gonna add my imaginary parts, and then when I write it, I just write it in the form of A plus IB. All right, I just write it in the form A plus IB. All right, same thing here. If I have a constant out in front, again, I just distribute that constant out. Same principle here. So C gets distributed to both the real and the imaginary part. All right, and then finally, if we're just trying to find the magnitude of it, right? So A squared plus B squared equals our C squared, right? We can then look at the exact same concept here, breaking apart A and B and understanding that that's going to be the square of our imaginary, okay? Or our complex number. All right. So it's important to know that vectors are not numbers, okay? So yes, they utilize numbers, but vectors are a representation of direction and magnitude, okay? There are representation of direction and magnitude, okay? So as a consequence, we cannot multiply or divide vectors, okay? We cannot multiply or divide vectors, all right? But a new thing, kind of fun, complex numbers, since they are numbers, they can actually be multiplied and divided, all right? So if we look at this here, we've got complex number 1 and complex number 2, again, just in the general form, difference being the 1 or the 2 here, okay? We can find the product of these two here by multiplying them together, all right? And essentially, what we're gonna do is just FOIL it out, right? FOIL it out like we've been doing for everything, okay? And once we FOIL it out, we get our terms like this, okay? And then we put like terms together, right? We put like terms together. So A's, there's no other value here, and we just kind of rearrange. So this B1, B2 come next to each other, and we're left with I and I, all right? And if we remember from way, way back, okay, I squared gives us a value of -1. I squared gives us a value of -1. So in this next step here, we can replace our I squared with a -1. Okay, we can replace I squared with -1. So then if we rearrange this based on real parts and imaginary parts, okay, only this value in the middle is the imaginary. Okay, it's the only one that still has an I left. So what we're going to do then is we kind of chunk them together. So we've got A1 times A2, and that's going to be subtracted now because we've got a negative value here from this quantity of our B's multiplied together. All right, so what this essentially will break down to is that this will give us a real part, and this will give us our imaginary part. All right, again, assuming, because A and B are just coefficients. So we're going to have A times B2, B1 times A2, and then those guys get added together. So again, we'll end up with our form of our real part plus our imaginary part. All right. And then if we look at here, we can deal with complex conjugates. Okay, we can deal with our complex conjugates. All right, and so a complex conjugate can also be written as Z bar, right? So, or letter bar, right? So if our original is Z1, okay, our complex conjugate is written as Z bar or Z1 bar, right? Where this just line straight above it, okay? And what we can do there is we can use the properties that we have been for complex conjugates and figure out what that would look like here. All right, and what that's gonna look like is we've got our A squared plus our B squared, because if we actually do this product, right, we multiply this out, we FOIL, and we cancel out, all right, we are left with just our A squared plus our B squared. Again, because we have the same values, they're just different signs. So again, those signs cancel out in the middle, and we're left with our A squared plus our B squared. All right, we're left with A squared plus our B squared. That's going to be our product. All right. And we've talked about this a lot here earlier, but we can also do dealing with the quotients, okay? Dealing with quotients here, right? So, for example, if we have Z1 over Z2, right, and Z2 is a complex number, we talked about multiplying by its complex conjugate, right? And that's what this is saying here. We multiply by the complex conjugate of the denominator on the top and on the bottom, because this is essentially like saying multiplied by 1, right? This is essentially saying multiplied by 1. All right, and if we do this, okay, what we can then get is this down here, this Z2 squared, right? That's going to end up giving us a real value here, and so it simplifies our denominator, and we can then continue on with our operations. All right. So then, if we were to actually go through this here, okay, if we were to fill in the blank, I'm hoping I can just have it. There we go. All right, perfect. So again, barring that I'm trying to go quickly here, all right, all you would do is FOIL this out, right? We could FOIL this out, and then remembering that I squared, right? So 3i times negative I, right? That turns into a -1. I squared turns into -1. So we can simplify this again, clumping our real parts and our imaginary parts, okay? So we end up with 11 plus 10I. Right? For this one here, we're looking for the complex conjugate of 4 minus I. So that's going to be 4 plus I, right? That's going to be 4 plus I. All right. So then if we do this now and we take this value and we square it, what it's asking us to do here is it's asking us to look at our original and our complex conjugate. Okay, so again, I may have skipped this in the beginning, so let me mention it now here. If you see these absolute value bars when we're dealing with these complex numbers, it's asking you to multiply by the complex conjugate, right? It's asking you to multiply by its complex conjugate. So when we see 4 minus I and they're in bars and that's squared, it's saying 4 minus I and 4 plus I. Multiply those together. All right. And we know that when we do that, we're going to end up with just one real number. We're going to end up with one real number, and that's going to be our 17 here. All right. So that's why when we multiply these guys together here, we're going to be left with our 17 on the bottom. We're going to be left with a 17 on the bottom here. All right. And just pick one at random here. Woo, I'm so smart. All right. So then we're left with 17 on the bottom, and we multiply this guy by its complex conjugate. All right. And the complex conjugate would be 4 plus I, right? So this would change this value up here slightly. So this would end up having to be 2 plus 3I multiplied by 4 plus I. So that's the difference here, is it's not going to be this minus 3. It's going to be just a minus 3 by itself. So instead of doing 8 plus 3, we're going to do 8 minus 3, right? And down here, same thing here. Since this would be a plus I, right? We would shift that around. Okay. So again, just kind of knowing that difference there. All right, but not super difficult. I know I flew through that, but again, take some time to really dissect that on your own. Okay. And as we've highlighted, there's a ton of benefits to switching to polar coordinates here. All right. But one of the really extreme benefits is, again, dealing with complex numbers, because originally when we were dealing with complex numbers, we were talking about them in terms of graphs on our XY coordinate. And mostly we had referenced them as when we were solving for our X values. And so we would say, okay, if your X value or your X-intercept, if your X-intercept was a non-real number, right? If it was a not real number, then we couldn't show it. And so now we can look and see, okay, well, what happens if we look at our complex numbers using our polar coordinates here? Okay, so we have our 3 plus our 2I. And we mentioned this in the beginning here, but again, we can represent our real part as our X part and our imaginary part as our Y. All right, so when we have 3 plus 2I, we go to the vector 3, 2, because again, real is X, imaginary is Y. Okay. Now, if we take this and superimpose a set of polar axes, okay? Again, we just turned it from our XY, right? We turned it from our XY graph that we're used to into a polar graph, all right? And what we can see here is that we can solve for our triangle to figure out our radius here. All right, so we can figure out our radius by doing a squared plus b squared and taking the square root, right? Pythagorean theorem. All right, so we get the square root of 14 here. All right, and then what we can do is we can use our tan function, or technically our inverse tan function, to figure out what the angle of 2 over 3 is, right? So we can figure out the inverse function for tan of 2 over 3. All right. And then, of course, it's complex numbers, as we said, are determined based on this value of a plus IB. All right. And again, we can show this here. So you've got your A coordinate plus your IB coordinate. All right. A plus your BI, and tangent is normally here B over A. All right. Again, keeping it in terms of generals for us. So we can have A plus IB, same thing, A plus IB. All right, so again, doesn't matter where it is, depending on obviously the values that we get, but it's gonna be this general form here, okay? So then moving forward here, the polar form of a complex number, okay? So using these values here and understanding our normal relationships with our X and our Y coordinates here, all right, we can remember that X is equal to R cosine theta and Y is equal to R sine theta. Again, this was our general rule. We literally just covered it in Algebra 2 today as well. All right, so we can remember these general rules here. And so we can rewrite our original complex number, right, where it says Z is equal to A plus IB. All right, well, we can replace our A and our B, or effectively our X and our Y, right? We replace A with our X. We replaced B with our Y, and we still had to leave that I value, right? Because that's not represented in the X or the Y itself, okay? And so then what we can do then is obviously pull out an R from both of these, and so this is our simplified expression for our complex number. Okay, and writing our complex number in this form is called the trigonomic form of a complex number. All right, and obviously it makes sense because now we're using our trig functions of cosine and sine, but we're still dealing with real and imaginary parts. So that's what makes it the complex number of our trigonomic form. Okay. So then there's these things called our modulus and an argument. Okay, so a modulus and an argument. All right, so if we look at our expression that we just came up with, right, the non simplified form here, okay, we can look at the trigonomic form and we can look at the polar form, right? Again, the polar form just talking about the coordinates. So if we look at our coordinate form, we have r comma theta, right? So length comma angle. Same thing here, right? We have this in terms of our trigonomic form of our complex number. All right. And with both of these here, right, we talked about how r is equal to the square root of the a squared plus b squared. All right. Well, this r term is called our modulus. All right. It's called the modulus, and that's the absolute value of the complex number. Right. That is the length of our r. Right. So that's the absolute value of our complex number, and that's going to be our r term. Okay. Our theta, our angle term, is called the argument. Okay, it's called the argument when we're dealing with complex numbers, right? So the angle of a complex number when written in polar form is called our angle here. Sorry, it's called our argument. All right, so again, the angle of a complex number when written in polar form is called the argument. All right, therefore, by this definition of modulus, r is always positive, right? So even though normally we talked about this, right, you take the square root, you'd have a plus and a minus, it's always going to be positive in this case. All right. And I love it. The argument of a complex number is not unique. In fact, for a given complex number, there are an infinite number of coterminal angles that would work for the argument. All right. So again, that's the same thing we talked about with the unit circle here. Right, I can go round and round and round and round as many times as I want, and it's going to give me a lot of coterminal angles. Okay. So for this reason, okay, when we're talking and just in standard practice, we're going to stay between 0 and 2 pi. Right, we're going to stay within that 1 unit circle. Okay. And then, of course, obviously knowing that these two are interchangeable is going to be helpful for you, okay? Because if you're looking stuff up to get extra help or whatever, right, you've got to know that these two forms are interchangeable, okay? And then since they're interchangeable, we obviously have to know how to do some conversions here. And the first one we're going to talk about is converting between our standard XY, right, and our to our polar. Right, so we already mentioned it here, but again, remembering that our A coordinate is like our X coordinate and our B coordinate is like our Y. We can know this relationship here, and again, from this relationship, we can go forward, right? Same thing here. If we're going from rectangular to polar, understanding this relationship here, we can do that. Okay, so if I have this complex number square root of 3 minus I in polar form, okay, well, my A value is going to be, or sorry, they're asking us to express it in polar form. All right, our A value is going to be the square root of 3. Our B value is going to be a negative 1. All right, so if we look at expressing this in our polar form here, okay, our B value is negative 1. So we're going to use our conversion formulas to find our R value and our theta, right? So our modulus and our argument. All right, in order to do this, we simply plug in our into our equation for R, right? So we have our A squared, which is square root of 3, and we have our B squared, which is negative 1. We square both of those, we add them together, we take the square root, and our R value can be plus or minus 2, right? And again, we know that we're always going to have a positive R value, so our answer there is going to give us a 2. Okay. In order to get our argument or our angle, right, we have to use our tan theta equals B over A, which is that negative 1 over square root of 3, right? We can, okay, we can plug this into our calculator if we need to, or we can use our understanding of our reference angles, and we'll be able to figure out that this angle has to be in the fourth quarter, or I'm sorry, the fourth quadrant, and in that fourth quadrant, it has to be the angle of 11 pi over 6. Again, using your reference angles for understanding the tangent function, okay? So in polar form, it could be either in our coordinate form or our trigonomic form. All right, so both of those answers are correct here. All right, and again, they are noticing here that another solution involves negative 2, right? So again, if you're involving the negative 2, you have to be in the opposite quadrant that we were originally in. So your answer would be in quadrant 2 here. But you'd face quadrant 2 and then walk backwards our unit of 2 here, okay? So again, I personally suggest when possible, try to stick to the positive values here, but it is also a solution that is plausible, okay? Then we have to express our complex number in standard form, okay? In standard form. So understanding what form this is here. Okay, so what does this actually mean? If we look at our solution for this one here, okay, we'd understand that our angle is pi over 6. Okay, we'd understand that our angle is pi over 6. And what we can do is evaluate sine and cosine at this pi over 6 function, right? So cosine of pi over 6 gives us the square root of 3 over 2. And sine of pi over 6 gives us this 1/2, all right? And again, all we do is we carry out algebraic processes, making sure we don't combine these because of this I term right here. And so when we simplify, we just get square root of 3 plus I, all right? So again, hopefully not too terribly difficult as long as you understand what these values for cosine and sine are of our reference angle, okay? And then obviously here, there's practice problems for you guys to try. They don't give you a whole lot, so I want to leave these for you guys. But again, it's exactly what we just walked through on the last page. So use those equations. You don't have to memorize them. Just know how to apply them. All right. So then kind of to sum it all up here, we reminded ourselves of what complex numbers are. It's got that real and the imaginary part, okay? And we can treat them like we treat vectors. Okay, we can treat them like we treat vectors. So we can add them, we can multiply them by a constant, and we can look at its complex conjugate, okay? And we can also then look at the product and the quotient. Okay, we can look at the product and the quotient and utilizing those properties of, again, the complex conjugate. All right. And then we talked about converting from into polar form, right? So getting that into a coordinate for us where we have R and theta, where R is called this thing called the modulus, and theta is our thing called the argument. All right. And then obviously we have a conversion formula from our polar to our trigonomic form, right? And so we can go either in the coordinate form or the trigonomic form, again, both used interchangeably here, all right? And then obviously understanding how to actually apply that and to go from polar form to standard form and to go back and forth between polar and rectangular coordinates, okay? So then moving forward to our checkup here. All right, so obviously it's going to be a lot of practice problems. At least try a few. Okay, at least try a few. And for the rest of these here, okay, it's asking you to, obviously you've got to figure out what the coordinates are, and then it's asking you to draw it on the plane here. All right, and again, we said our x-axis is our real part, our y-axis is our imaginary. So take that and run with it here. And remember, things like -5, right? It still has an imaginary part. It's just plus 0i, right? It's just plus 0i, or same thing here, right? It's 0 minus 2i. So your real part for this one is 0, okay? So use that. And then obviously writing these complex numbers in polar form so that you can put them on the graph here, right? They're in a bunch of different forms, so figuring out what does that mean and what does that look like, okay? And then identifying these different points, okay? So realizing what the angle is, and working backwards from what you know, all right? Working backwards from what you know. And if I take a look here, so notice A is on the 1, 2, 3, 4, 5, 6. It's on the 7th ring, okay? So this R value here is going to be 7, all right? And if you look, it's at the angle 3 pi over 4. So not too terribly difficult. You just have to count the number of rings, and that's going to give you your R value, right? So our R value again was 7. And then we have cosine of 3 pi over 4 plus our imaginary part I, sine of 3 pi over 4. Okay, again, so you can do that for all of these. So knowing how to do that is going to be super important. And obviously we have a quiz here, okay? So that wraps up really polar form of our complex numbers. Again, you got one quiz so far, all right? And if we keep moving forward here, okay, we can do math of our complex numbers. Okay, we can look at math of our complex numbers. All right, and they're saying this math isn't complex, but I'm ching, right? So we're dealing with complex numbers, but just because we're dealing with that doesn't mean it actually is a difficult or time-consuming process here. All right, it's just a matter of paying attention to detail. All right, so on other hands, you will see that multiplication and division of complex numbers is vastly simplified when you work in polar coordinates, okay? So again, a benefit of polar coordinates here. And we did talk about this in the last unit, so it's kind of a nice reminder / more details. When we're doing addition, okay, when we're doing addition, right, we talked about treating it like a vector. Okay, we talked about treating it like a vector. So again, you add your real parts and you add your imaginary parts. All right, that's how this would work with our complex numbers. Okay, and in the polar form, right, in the other polar form, it works the exact same way. Okay, so if it's not just this A and this B, if it's in the trig form, right, if it's in our polar form, right, especially this is the trig form here, okay, we can add it together, right? We can add it together as well. So if we have Z1 plus Z2, we group together the we group together our A values, which is dealing with cosine, and we group together our sine values, which is dealing with our Y, right? And so we can add these together if we had real values, okay? We could add them together. And use all the rules we've been developing throughout this course, all right? And again, when we're dealing with addition, okay, we can do this head to tail method because again, this is the head of one arrow and it's matched up with the tail of this dashed arrow, all right? We can do this head to tail method where again, you put the the vector, you put this vector on top of its other guy, and you put this vector on top of its other guy, and it'll match up with what the actual sum of those two vectors are, right? And it works the same for complex numbers here, because again, we're representing our complex numbers on our polar coordinate as vectors, okay? So we can actually do this here. And then obviously that line from our origin, or our pole, as we call it in polar coordinates, from our pole to that combined spot, that's where this actual addition is occurring. All right. And then if we do subtraction, lo and behold, it's going to be similar, right? We group together our A parts, we group together our B parts, or our cosines and our sines. All right. And then again, remembering that we can do the head to tail method. But what this looks is a little bit slightly different. We show the difference between Z2 and Z1. Okay, we show the difference between Z2 and Z1. All right, so this little dashed blue line here, dashed blue line, if we take it and we draw it from the pull down, it gives us our difference, right? So that's our difference vector, the difference between Z1 and Z2, okay? So then here, if we go and we look at some of these practice problems here. There you go. Okay, so our answer for this is going to be 2 plus 8i. All right, and again, 3 minus 1 gives us 2. 5 plus 3 gives us 8. All right. Now if we have to plot these, okay, we have to plot these on the plane. Okay, we can show our 3, 5, negative 1, 3. Again, remembering that our x-axis is our real part and our y-axis is our imaginary. So that shouldn't be difficult. We plot them on our axes, and then remembering our head to tail method, or being able to go up here to our addition and just draw that product itself. So they show you both, right? The blue line here is this 2 plus 8i. You go over to up 8, or again, you do the head to tail method where you can show the dashed lines here. So again, this dashed line is representative of this 3 plus 5i vector, and this dashed line is representative of this negative 1 plus 3i. Okay, so we can do that here. Now, if we were to look at this guy here, all right, what we can see is all we have to do is figure out what the values of these different angles are, right? So again, this is where knowing your unit circle and your reference angles is going to come in really good handy. So again, we're dealing with essentially two angles here. We're dealing with pi over 3 and 11 pi over 6, all right? So that's what we're dealing with here. And what we notice is the first step is obviously to change from our trig functions into their actual values. Okay, so we simplify everything down, right? And so that's what we do here. And then you're going to notice that we collect like terms. Okay, so we collect like terms. Oh, apologies. We first have to distribute. So we had to distribute first. All right, but after we distributed, then we collected like terms. So we had the real parts and the imaginary parts together. So the real parts were together, and then the imaginary parts were together. All right, and then we were able to simplify that down potentially if we wanted. Okay. Now we can easily show these guys on our polar graph, because again, they're written in terms of our degree, or I'm sorry, our angles in radians. So what we can do there is we can find the angle and go up however many coordinates. Again, the coordinates being the constant out in front. So 4, okay, we go up to the 4th ring. So 1, 2, 3, 4, and we go over to our angle pi over 3. Okay, so that's how we get there. All right, this guy here is at ring 1. I'm sorry, it's at ring 2, 1, 2. And it's actually a negative 2. All right, it's a negative 2. So we have to go to 11 pi over 6, which is here. So we face 11 pi over 6. And since it's a negative value, we walk backwards by 2. Okay. So again, that's how we got there. And to show the additive function, we can do the head to tail method or understand this process here, and we get to our new vector. Okay. Awesome. Okay. So this one here is talking about addition and subtraction. And this is showing you that if you have a difference here, you can break it down and look. And you can, again, of course, it's either talking about having the additive effect or a subtractive effect. All right. So both of those kind of work there. And again, this one is saying as well that, remember, we started with a -2, right? We had a -2 of our cosine of our angle here. So we went backwards. So when we have a +2 and we go forward with the angle that we have. All right. So there you go. All right. And there is a difference here. Okay. All it's doing is it's flipping, right? We're flipping. Okay. So then if we look forward here at the product of complex numbers, okay? Again, we're going to multiply it out just like we would with vectors. So we'll do our foiling, we'll combine like terms, we'll simplify as we can. Okay, so then we have to be able to interpret this geometrically, and what does it actually look like? Okay, so if we look at polar products here, all right, we've got two angles. First off, we've got two vectors. We've got Z1 here, which is in blue, and we've got Z2, which is in red. And again, both of them are in this trigonomic form of R times by the quantity cosine squared plus I sine squared, right? They're both written in that trigonomic form. Okay, so what we can do then is we can use our property, right? We can FOIL them out, right? And again, it gets a little bit tedious here, but we can pull out the values here. We can FOIL out everything. And something I'll point out that they did, since R1 and R2 were already pulled out, they're already factors on their own. All this did, this first step, was it moved R2 next to R1. Okay, we don't need to redistribute that back out. That just makes it more complicated. So leave that out. It's like a factor on its own. So you'll pull R2 out here. And then here we have our two functions in terms of cosine and sine. And then this next step here shows the foiling. All right, this one shows the foiling. This one shows the combination of our real part, right? I know it's really long here, but this is the real part, and this is our imaginary part. Okay, this is our imaginary part. Okay, and then what we can do here is we can obviously simplify it down using our understanding of our trig functions here. So if we have cosine and it's multiplied together, right? If we have our cosine of theta here, so we've got theta 1 plus theta 2, okay? That is equal to our expression right here of cosine minus sine, okay? And remember back to our trig functions of like cosine of 2 theta, right? Cosine of 2 theta, this is very similar. All right, same thing with sine, right? This is sine of, it's like sine of 2 theta, all right? So we can use this understanding here and just replace back in. So this first part here gets simplified down to just cosine of theta 1 plus theta 2. Okay, this second part here gets condensed down to I sine of theta 1 plus theta 2. Okay, so very simply here, we can add them together, then take our sine or cosine function, and we have our expression. Okay, so we know that we can get it all the way down to that last expression there. Okay, so then if this is our new expression here, geometrically, what this means is that the product is determined by the vector whose angle is the sum of the given angles, right? We know that, right? So we've got to add angle 1 to angle 2, right? So when we add them together, we're down here even further at a larger angle. Okay, so we added angle 1, we added angle 2 here. All right, so that's our angle. And then for our R value, we have to multiply them together. So this is not R1 or R2 alone, it's R1 times by R2, right? So again, if this was 2 and this was 3, this would be a 6 value here, okay? So if we're looking at this, okay, if we're looking at this, we have Z1, we have Z2, and we can simplify it down into this equation. We don't have to use the big long one or prove anything. We can just use that equation directly. So what we can do here is, of course, R1 is 3, R2 is 6, or I'm sorry, R2 is 2. Okay, so those multiplied together give us the 6 value. Okay, and then I've got cosine of angle 1, which is 7 pi over 6 plus 2 pi over 6. So we write those together. Same thing here for our sine function. So that gives us 11 pi over 6. So then this is asking us, what's our cosine and sine of 11 pi over 6? All right, and using our knowledge of our unit circle here, we're able to replace those with the exact value. All right, and we've got it multiplied by this quantity of 6 here. So then obviously the final step for us is to distribute that 6 back out. And so we're left with 3 square root of 3 minus 3i. Okay. So then if we wanted to calculate this by converting to standard form, then we can take the product. Okay, so we could have converted this into standard form here and then taken our product. So again, here, convert to standard form, out, multiply out. Here, we convert it to standard form by replacing cosine of 2 pi over 3, right? And sine of 2 pi over 3, so we replace it using our unit circle, multiply it out, and then we can still do the same thing. We take these two that are now in standard form and we multiply them out using our FOIL method. Right, FOIL, combine like terms, simplify I squared into -1, and then simplify your expression. It's going to give you the same answer here, right? So again, you could do either way. You could do both ways, whatever you're comfortable with, unless you're told that you have to do it a specific way, right? So you can do either of those, and it's going to give you the same exact answer. All right. So then, of course, this is showing you all the different parts here. So if this is Z1 in red, we go all the way to here. All right, this was Z2 directly to this blue guy here. All right, and then obviously to get the product here, we had to go with all of Z1 plus our little portion of Z2, so that gave us here. And then as we mentioned earlier, our R value is now those quantities together, right? So it's not 2, it's not 3, it ends up being our 6 value. Okay. Apologies. Okay, so then moving forward here with complex conjugates and division, right? We love it, we live it, we learn it. Okay, so we can denote those in general by having that Z bar, right? So we can denote them by having that Z bar. All right, so this is saying here that Z is equal to A plus IB and Z bar is equal to whatever the, again, it's so, I don't know why they did it, it's kind of funny, but this is saying the complex conjugate of this value of A plus IB, right? And the complex conjugate of that is A minus IB, all right? So if you ever see it written like this with a bar over it, that's asking you for the complex conjugate of what's underneath it, all right? It's asking you for the complex conjugate of what's underneath it, all right? And regardless here, remember when we multiply by a complex conjugate here, we're able to cancel a lot of things out, so we're only left with our A squared plus our B squared value, right, in our denominator. And then on top, we just FOIL like usual. We combine our real parts, we combine our imaginary parts, and then this is what we're left with, okay? So if we do a quick practice here, just computing, we've got -1 plus 4i over 5 plus 12i. Okay, so again, the complex conjugate for this would be 5 minus 12i, right? We multiply by 5 minus 12i on the numerator and the denominator. Okay, on the denominator only, if we look there, okay? We FOIL that guy out, we're gonna find 25 minus 144i squared. Okay, well, I squared turns into a -1, so that becomes plus 144. All right, then here, we've got 12 -12 times 5 and 5 times +12. All right, so those guys are essentially going to cancel each other out and give us a 0, so we're going to have plus 0i. right? So this bottom here is just going to be our a squared, which was 5, plus our 12 squared, which is that 124, or sorry, 144. All right, so again, essentially it's going to turn into this 169 here. All right, then again, we get to our top and we're multiplying by our complex conjugate. So we're just foiling out. So FOIL, FOIL, FOIL. Again, change I squared into -1, right? Combine your real parts, combine your imaginary parts, and we're left with 43 over 32, or sorry, 43 plus 32I over 69, 169. All right, and what we can do here then is we can have both of these values be put over 169. So 43 over 169 plus 32I over 169. So this then gets written in our complex number form of our A plus our BI, right? So we can do this here. And a lot of times when we do write it like this, we're going to be able to simplify one, if not both, of the numbers here. So again, that's a benefit. Okay, so if we do division of complex numbers, right, it's gonna simplify greatly here. Okay, it's really gonna simplify. So again, looking at our expression of Z1 and Z2, when we do our quotient here, all right, we're gonna do the same thing where we multiply by our complex conjugate. All right, so we're gonna multiply by our complex conjugate here. All right, and of course, what's gonna cancel? It's gonna cancel, so we're left with just an r squared on bottom. Okay, we're left with just an r squared on bottom. So again, actually, I apologies. I misspoke here. All right, so we don't even have to do that at this moment here, because if we skip that kind of, essentially, right, we understand that that's the process, but what this simplifies down to for us in terms of polar coordinates, it actually skips a step here, and it even becomes more simple, right? If we have Z1 over Z2, right, understanding that we're going to multiply by the complex conjugate and all that fun stuff, this turns this equation into Z1 times Z2 over the absolute value of our Z2 squared, right? So the positive version of that, okay? So if we look at this here, we then have our R2, right? Since we're dealing with Z2, and we have the same function. All right, we have the same function. And we can then, of course, again, change, and we're left with, at the end, R1 over R2 in our simplified form. Again, combining our cosines and sines, and we understand now that this will simplify further based on those relationships we talked about earlier. Okay, so it will be simplified into this cosine of theta plus theta, or in this specific example, since we have negatives now, right, we have negatives, we can do a subtraction between them, right? We can look at the difference between them. Right, so earlier we talked about adding them together. Now we can talk about actually subtracting the two angles from each other. All right, so then looking at our final quotient here, we're left with this. All right, and what this means geometrically here, it's that the vector is determined, the angle is the difference between the numerator angle and the denominator angle. Right, so we take Z1 minus Z2, right? We take Z1 minus Z2, so we take the difference between them, all right? And that gives us our new angle here, all right? And the magnitude is the quotient of the given magnitude, so we take R1 and we divide it by R2, all right? So, of course, like we said, here's our value, so we want to calculate out first, and we want to just use this formula here so we can jump immediately. Those earlier slides were basically our proof, right? We were walking our way to this expression, but now that we have this equation, we don't have to redo that. We can just jump straight here. If we know that this is, we're asking for Z1 over Z2, we just come right here and we plug into our equation here. So we've got our R1, we've got R2, we've got our angle 1 and angle 2 here, right? So we can plug those guys in. And then simply when we do our subtraction here, we're left with 3 pi over 6. All right, so then when we've got 3 pi over 6 is our angle, we replace our values of cosine and sine for 3 pi over 6, and then we can simplify that out. All right, and we're left with 3 over 2 times 0 plus I, right? And normally we would distribute that out to both of those, okay? But obviously 3 halves times by 0 gives us 0, so technically this complex number is 0 plus 3I over 2. All right. If we wanted to convert to standard form first, instead of just using that equation here, what we could do is, again, just replace the values for our set angles using our knowledge of our unit circle, and then we can simplify down our complex numbers. Then we can actually write out our complex numbers. Okay, we could write out our complex numbers. We'd have to multiply by its complex conjugate on the top and on the bottom. And then we could continue to simplify down, right? So combining these, understanding that the I squareds turn into 1, -1, right? All of that fun stuff. And then doing the same thing on the top here. And then we can be left with, eventually this will turn to 0, right? This will turn into 6. And we have a value of 4 here. So we would give 0 divided by 4 and 6 divided by 4. So again, still we're left with this 3 over 2I. Okay. And then of course, geometrically, here's the quotient. So we started with our angle blue and red, and we took the difference between them. Okay. And it gave us this angle here of green, right? And it gave us that new angle between them. And then our magnitude here is determined by our R value. All right. It's determined by our R value. All right. So in general here, here's kind of your summary. All right. So understanding that earlier, again, those were just the proofs to get us to this point here. So you can just jump straight here to use these equations. As long as you understand and you have your complex numbers in this trigonomic form, as long as it's in trigonomic form, you can use this and go ahead with it. Right? And then based on that, you can plug it into these two equations here, the product and the quotient, and you can calculate out what those means here, what those mean. Wow. Ooh. All right. And again, geometrically knowing what that's going to look like in terms of your graph. So obviously this is the angles added together. This one would be the angles subtracted from each other. All right. This would be the magnitude of multiplied together, and this is the magnitude of obviously the division. All right. So pretty simple stuff here. Okay. Of course, this practice, I'm going to ask you to do that, all right? It's really, really good for you. Please make sure you try it. And that pretty much wraps up this unit here, okay? That pretty much wraps up this unit. So again, talking about, again, complex numbers can be treated like vectors, and understanding the coordinates as they are, and then understanding those kind of relationships and algebraically expressing them. Okay, and of course we talked about like the sum of the two vectors using the head to tail method, the difference being the subtraction between them. All right, and of course understanding complex conjugates in general, right? So combining was the first one here. Okay, and then we talked about understanding the complex conjugates in order to do some of our properties here. Okay. Again, a lot of good practice problems for you, a lot of good notes, so please make sure you are filling those out, okay? And then finally, our checkup, which again is going to be a lot of just practice problems, okay? Again, do a couple of them at least, so that way you can feel confident going in. But again, reminder, I feel like this should be super, super simple for you guys, because it's asking you add, subtract, multiply, find the complex conjugate, right? Do the division, right? All of those things here, okay? So hopefully it's not too terrible, right? Hopefully it's not too terrible. So please make sure you take some time and go through these ones here, and just understand the notation, right? So again, this is saying Z1 divided by Z3, all right? You can still use the equation for Z1 over Z2. They just try to trick you with a 3 instead of a 2 this time. It's the same thing, okay? And then doing very similar things, but now being in the trigonomic form, all right? Now being in the trigonomic form, asking you to still do that, okay? And again, more practice problems, beautiful, lovely, okay? And then they are asking you to convert to polar form and then calculate out different things now that you're in polar form. So again, pretty much, I think it should be straightforward here. All right, and that brings us to this quiz here for 6.4. All right, so right now you've racked up a quiz for 6.3 and a quiz for 6.4, and oh my goodness, we are able to get to it. So no weekends homework, woo! All right, if we look at powers and roots of complex numbers here, we got 30 minutes, we can do it. All right, so we're gonna look at taking the power and the roots of complex numbers. All right, so if we were to look at this here, all right, first off, again, we're still dealing with our real part plus our imaginary part, okay? And if we look here, all right, obviously anything to the power of 1 is, or to the power of 0 is going to be 1. Anything to the power of 1 gives itself back, all right? And then when we start doing z squared, right, we have to do the foiling here. All right, and we can start distributing all this out here. And hopefully you're going to notice a very similar pattern that we talked about in first semester, right? We talked about it in first semester in terms of X and Y here, but now we're talking about it in terms of A and B. So notice the pattern here that this is asking you for Z squared. So we start with A squared, and we work our way down in terms of the powers of A. So this is A to the second, A to the first, A to the 0th, because technically that's 1, right? And we go the opposite direction for our B terms. So we start off with B0, B1, B to the power of 2, right? If you don't believe me, let's check it out with Z to the 4th here. So according to this logic, we should start off with A to the 4. So we go A to the 4th, A to the 3rd, A to the 2nd, A to the 3rd. Oh my gosh, I'm sorry, A to the 1st, A to the 0th. Right? So that trend holds true. Then we look and we see, okay, we look and we see here, okay, what happens with B? B should start with B to the 0th, B to the 1st, B to the 2nd, B to the 3rd, B to the 4th. Oh my gosh, we're geniuses. All right. And then we also have to look at the coefficients here. Okay, we have to look at the coefficients. So hopefully you might notice a pattern as well that, again, if I have a 2 there, my coefficient's going to be a 2 or start with a 2. I've got a 3. I'm going to start with a 3. I've got a 4. I'm going to start with a 4. Right? And as we start to get larger, we're going to have terms in between there. And we'll talk about what that means and what that looks like. Okay? But essentially, the same pattern rolls out for polar form. The same pattern rolls out for our polar form here. Okay, and it's even simpler in my personal opinion. I love it. It's great because, again, we talked about how when we FOIL this out here, if I've got Z squared, we talked about how we can just condense it into R squared out front. We have cosine of 2 times our theta and 2 times our theta, right? So that's all we do here. All right. If we bring this to the 3rd power, it goes R to the 3rd and 3 theta. To the 4th power, R to the 4th, 4 theta. Again, I hope this is like a breath of fresh air at the end of this semester. All right. So literally for this year, it is a specific theorem. All right. And it's saying that Z to the power of n is equal to R to the power of n times by cosine n theta plus I sine n theta. Right, so whatever this exponent is, you use it for this R value and you use it to multiply by your angle here. All right, so looking at this here, if Z is our complex number with a magnitude of 2, okay, so it's saying our R value is 2, and our argument is pi over 3. Again, realizing that argument is talking about our angle, so it's pi over 3. All right, so we're dealing with this right here in red, okay? It's saying the 6 consecutive powers of Z will have an argument by, again, all it's saying here is if we look at the power. So the power of 2, 3, 4, 5, 6. Okay, 2, 3, 4, 5, 6. And the reason that's possible here is because all we did is we took this angle, multiplied by 2. Took this angle, multiplied by 3. Multiplied by 4, 5, 6, right? And it goes around in our polar coordinate here. All right, and hopefully you're going to start to notice here that it looks like it's repeating itself, and that's how we get these beautiful repeating flourishing graphs in our polar coordinates, is because of this relationship here, okay. It says, notice that z squared has a magnitude of 4. Again, that's what we talked about here, having, since it's a magnitude of 2, it would be 2 squared, 2 to the third. But obviously all these other ones are too large to represent on the graph. So if you ever see like a dashed line that keeps going, that means that it's too large to be represented on the graph, right? If there's a real value, it's just too far out. Okay. So again, I will let you guys practice this here. Really, the key is of course understanding that relationship. All right, understanding that relationship and just paying attention to detail. Oh wait, this one's not a practice problem. So if we look here, we're going to convert to polar form and then execute this raised to the power of 18. So first off, we'll convert here, right? And we just use our two equations. We know our R equation, and we know our tan theta in order to get our angle. Okay, so once we've done this, we realize that our R is going to be a value of 4, and we're dealing with an angle of 5 pi over 6. All right, so we can rewrite it in this trigonomic form right here. Okay, then what it's saying is evaluate this, right? Compute it to the 18th power using his theorem. So if we look at the calculation here, what we're being asked to do essentially is right here. So we're taking R to the 18th power and we're multiplying both of our angles by 18. All right. And so once you do that here, you get this really large number. I think that's 68 billion. All right. Times by cosine of 15 pi plus I sine of 15 pi. All right. And again, cosine of 15 pi gives us -1. Sine of 15 pi gives us 0, so this simplifies down to this negative 68 billion. Okay, 68 billion. Jeez, that's a big number. All right. So then again here, if we were to write this in our standard form here, we would do our conversions. All right, we would do our conversions, understanding that 4 is our R value. Okay, our angle is 20 degrees, and this, since it's raised to the third power, okay, since it's raised to the third power, we're going to multiply that by 3. Okay, we're going to multiply our R value by, or sorry, raise our R value to the third power and multiply our 20 degrees by 3. So we're left with 64 times by cosine 60 plus 64 sine of 60i. All right, or this cosine and sine without the 64s could have been in the parentheses. And regardless, though, we can simplify this down here because cosine of 60 gives us 1/2. Sine of 60 gives us this square root of 3 over 2, right? And again, to simplify that down further, you'd execute those problems, and we're left with this 32 plus 32i square root of 3. All right. So that's our standard form here. Again, just simply filling in and solving for the problem. All right. Looking at our modulus here for this cosine of pi over 2 plus I sine of pi over 2 raised to the 5th power. It's saying, what is the modulus, right? What is the R value? And if you notice here, normally there would have been a constant out in front of this indicating our R value, but since there's no constant, we assume that value is 1, right? As of course, right? We assume that our modulus there is 1. So 1 raised to the 5th power is still going to give us this output value of 1 here. It's still going to give us this output value of 1. So then again, if we're going to write this in standard form, we're going to use the knowledge that our R value is 1. I wish it would have showed us the equation here. But again, all we did was we plugged in, so we had 1 to the power of 5. We multiplied both of these by 5, and then we figured out the replacement values for them and simplified. Okay. And then if we want to take the roots of a complex number, right? Again, talking about the nth root, because if we say the 3rd root, 4th root, 5th root, we call it the nth root. So we can do that for a lot of them, okay? And so what we can do is we have this rule: the nth root of a complex number z is any number v equals a plus ib such that this is true, okay? So again, just working backwards, right? Just working backwards here. All right. And again, it looks a little bit strange here. And again, since there's no root, it's just talking about a power, but we can use the theorem from before to be able to figure out the roots of complex numbers in its polar form. All right. So using that here, we can convert that equation that we saw, and we can then solve. And so this is what we're left with in terms of finding our nth roots, right? So we take it from something abstract to something that we can actually do in our polar form here. Okay, and so we're left with, if it's asking you for the nth root and we are in our trigonomic form, we can then just take this as the nth root of r, right, our r value times by cosine, and we go theta plus 2 pi k over n plus 2 pi theta over n. All right, again, k is going to be integers, right? Starting at 0. So 0, 1, 2, 3, 4, right? Whatever it is, all the way up to potentially n minus 1. All right. So again, if this was 4, it would be all the way up to 4 minus 1. All right. So we can do that. And again, this n value is talking about the nth root. Okay. So if we look at this here, okay, we've got our z value. We're letting v equal this. Okay. We're letting v equal this. And this v here is an nth of z, right? Which means that z is equal to v to the power of n. Okay, so z is v to the power of n. That's what that's saying there. All right, so again, if we were to plug this in, it's saying z, right there, there's our z, and is equal to this guy here raised to the power of n. Okay, raised to the power of n. So then actually calculating this out here, using that theorem that we know and we love, this is raised to the power of n. So what we do is we raise s to the power of n, and we just take it and we multiply those inside angles by that value of n. All right, so this gives us another form of this equation here. All right, and if we think that s of n is equal to r and these are equal to cosine and sine, right, we can then understand how this is true. This holds true here. Okay, so again, understanding this principle here, we can replace our s with this root of the nth root of r. Okay, we can replace our n of this angle here with the quantity that we know, right? Same thing here. And again, this is how we get to that expression below, right? This is how we get to that expression that we know, or that's up here, that we know now, okay? So then if we look at things in terms of roots, so what does that mean geographically? All right, and right here is saying this is the formula for v, all right? And it shows the nth root of z have the same modulus. They have the same r value. Okay, that means that all of the n will lie on this radius. Okay, so they're all going to lie on that radius. Okay, and since k varies between 0 and n minus 1, we'll get values that are going to be coterminal angles. Okay, it'll be coterminal angles. Another way to see this is when you plug in actual values, you get out these different things. Okay, so that basically brings us to a full rotation of 2 pi. Okay, it should bring us all the way around to our full rotation of 2 pi. Okay, so if we were given this formula here, all right, and we were asked to calculate our 6th root, okay, If we were asked to calculate our sixth root, well, we know that this is our R value. We know that this is our theta value. Okay, so we can plug those in. And since it's the sixth root, our N is going to give us a value of 6, right? So we can do this, and we understand here that our K values are going to start at 0 and go all the way up to N minus 1, which is 5. Okay, so we're going to go all the way to N minus 1, which is 5. Okay, and so what this is saying here is that we're going to start out at, if we go and we plug in a 0 here, if we go and we plug in a 0, we evaluate this expression, all right, and it's going to give us this pi over 18, all right. We then can say that this is where we're starting, and we're at intervals of 3, or pi over 3. Okay, we're at intervals of pi over 3. And again, the reason we can know that is because we tested out a couple of different values, and we realized the difference between them is just an interval of pi over 3. So again, we'll start at pi over 18, move pi over 3, show another one, move pi over 3, show another one, move pi over 3, show another one, until we go an entire full rotation, right? And that's perfect. This is exactly what we're talking about. So at this value of V0, right, it was K was equal to 0 here. So this is where we start. We move pi over 3, we're up here for V1. Move pi over 3, V2, pi over 3, pi over 3, pi over 3, right? And again, that's how we get this repetitive nature here. Okay, again, seeing the difference between them, all right? And it never hurts if you are confused with this graphically, or you're confused with how do we know this interval here, you can plug in multiple values for your K, all right? But again, the one that I always suggest is you need to do at least V0 and one other point, okay? That's a good general rule there, okay? So then, of course, you guys can do these practice problems, just understanding, again, it's even telling you got to convert to polar form if it's not in polar form in order to use some of the theorems. All right, so convert to polar form, and then be able to sketch those roots and answer what's the modulus for different equations here. All right, then we can talk about this thing called roots of unity. And this stems from this fundamental theory of algebra, right? And this was, remember, we talked about it way early on, that a polynomial degree n has exactly n roots, has exactly n complex roots, okay? So again, if we had something x squared, we would have 2 complex roots, okay? We could have 2 complex roots. So moving forward here, if we look at the degree n in this polynomial equation, Vn equals 1. All right, so according to the fundamental theory of algebra, this will have n solutions. Okay, we'll have n solutions. All right, and these nth roots of 1, specifically 1, we call them the nth root of unity. All right, the nth root of unity. So it's all the complex numbers of root 1. And again, I try to reference it back to something we know. Unity has the word unit in there, like the unit circle that has a radius of 1, right? So again, these nth roots of 1 are called our roots of unity, okay? And then we can also find them using complex root finding techniques, okay? And basically here, they're all solutions to the equation here. All right, so we can plug these in and figure out what the values are. We can continue and look and look at the calculation, right? And again, all they're doing is plugging in those different values, okay? So we're calculating our 6th root of unity. We're calculating our roots here, all right? And we can check directly each of these numbers to make sure it has the property that it's raised to the 6th power when you get the number 1. So like V1 to the 6th, right, it should have that 6th power here. All right, and if we start to separate these out here, okay, we have this to the 6th power, right? Remember, one of our properties of powers is that we can raise a power to a power, right? We can raise a power to a power. So if we were to look at 2 to the power of 3, right, we can separate that out. Same thing here. If we've got something raised to the power of 3, we can separate this out into even further, right? So and then of course looking at its complex conjugate, we eventually get down to equals to 1. All right. So of course, being able to look at other values, and essentially what this is going to work out to be graphically is that they're always going to start at 1 for the nth root of unity, right? They'll always start at 0 for the x and 1, and there will always be n of them, right? So if this is the third unit of root of unity, there's going to be 3 versus 12th unit, it's going to be 12. All right, and then they're dispersed evenly about the circle. Okay, so again, they're even about the circle. All right, so that's a quick overview of that one here. All right, and then finally we have Euler's formula. All right, and this is if we're dealing with exponents here. So we're already familiar with the function f of x is equal to e of x. So we can extend this slightly further here. So if we're dealing with taking e to the power of our complex number here, all right, so e to the power of our complex number, we can just directly use this formula here. So e to the power of a times by cosine b plus I sine of b, right? That will give us a value here. Okay, so then if we look at this formula here, we don't have to prove it, hooray, right? So we don't have to prove that one. So all we do here is we've got e to the power of 0 plus pi, right? So we then reduce that down and we plug it into our formula. So we're left with 3 pi I plus 1 gives us 0. All right. And again, they set it equal to 0 here because we need our real part and our complex part here. All right. And again, E is a value that you can actually plug in. All right. E is an actual value that you can plug in. All right. And again, the way that he got this was distributing that E to the 0 to all of these. Okay. So figuring out what those values are here. All right. So then looking at our last study together, said, understanding, we talked about how we deal with powers and how it relates from things that we've already done into these complex numbers. Okay, so being able to do that, looking in this complex number form and looking in our polar form here. Okay, then we have this nifty theorem that helps us a lot, where we can then just, if something's raised to the power of n, we just use this replacement formula. Okay. So that's super helpful here. Then we talked about complex numbers and the roots of them. Then we talked about the nth root of unity. And we talked about the nth root of unity and what that's going to look like there. And then we talked briefly about Euler's formula here. So again, basically just being able to apply the formula the way that you see it. All right. And e pi to the I is equal to -1. Okay, so that's just a constant that's going to be helpful for you. All right. This checkup here, of course, is going to have practice problems for you to work through. So again, once you've gone through the practice problems within the lesson itself, make sure you go back here and you try some of these. Okay. So again, some of these are already in the polar form, and it's asking you to go to the standard form. Right? Some of them are then asking you to, of course, find the complex roots in the different forms and then sketch the roots of unity here. Okay, so not a whole lot with the unity stuff. All right, just being able to sketch them and what does that look like graphically. Okay, and so then, believe it or not, ladies and gentlemen, we have reached the last lesson. Okay, so that is our last lesson, 6.5. All right, so today we actually did get to cover the 3 that I wanted. So we covered 6.3, 6.4, and 6.5. So as of this moment here, when you finish those 3 quizzes, you are more than capable of moving on to lesson 6.6 here, which is of course just our unit test. Okay, so make sure you go through those reviews. If you would like, again, extra credit practice, extra credit discussion here, all right? And you have the mandatory CST, okay? You have your mandatory CST. Okay, so then that brings me to just kind of some final concluding marks here. Again, please remember that you have until next Friday to finish this. So you have time, but again, it's always better to get a jump start on it because you never know how long something might take you, okay? So that's kind of gonna wrap up though for us. That's gonna wrap up semester 2 of PreCalc. All right, so again, I'll send out an update on this weekend. I'll send out an update middle of the week next week, and then finally once your grades are done and calculated based on obviously 80% from Apex, 20% from attendance and participation, right? Then I will send those grades out to you obviously sometime next weekend here, okay? So you know you've got that stuff to work on. And then just a reminder here, once you are done with unit 6, you need to move on and do this semester 2 exam, okay? So you've got an overview, you've got a review, which again I strongly suggest that you do, and you're going to do only this first exam here. You're going to do the computer scored semester exam, okay? So do not worry about this second one. I don't know why it doesn't say TST on it immediately, but if you just click on it, it says teacher scored. So you only have to do the computer scored final for PreCalc here, all right? But of course, if you've got questions, comments, concerns, you can Google Hangouts me, Google Class me, a lot of different ways, forms, communication. And I'm just obviously here to help. Last kind of things here, I just want to say again, everybody, thank you so much for your effort, your participation, your willingness to try. Keep in the back of your head that remember you're doing this so that you can move up programs. So finish out this last week here strong, and of course, let me know when you need stuff. All right. I hope to see you guys very, very soon. Have a good day. Bye-bye.